The second application of parametric surfaces is finding the area of a surface. So finding the area of a surface S in a space. So we call it surface area. Okay, so let me give you a recall. When we have a region in R2, so where R is a region in two-dimensional space R2, then when we want to find the area of that, so assume that we have x-axis, y-axis, and then we have a region like this. To find the area of R, we can use double integral, and then the double integral of 1 over the region R. Just because we said that the double integral of any function would be the volume of the solid that is below the function f over the region R. Where the function is 1, basically our solid has the height 1, so that's why we just have the area of the region R. Now if we have a surface in R3, the area of that we can use the surface integral, and then we write the double integral of 1 ds over the surface S, where S is our surface in R3. Okay, so we have something like this: x-axis, y-axis, and then z-axis, and then assume that our surface is something like this. To find the surface area of S, we just need to do the double integral of 1 ds over S. Okay, so the question is this: what is ds? We're gonna derive ds when we talk about surface integral later on, but for now ds is the length of partial derivative of our parametric equation of our surface with respect to u, cross product with r with respect to v, du, dv. Okay, so if I want to kind of give you the summary of what we did, we say that for a surface S with the parametric equations of x of uv, y of uv, and z of u and v, where u and v is in D subset of R2, then area of S is equal to the double integral of 1 and then R with respect to U, R with respect to V, and then dA, which could be du dv or dv du, over D, where the region D is basically the domain of our parametrization. Okay, so that's how we find a surface area using parametric equation of our surface. Let's look at one example. For example, we're gonna find area of the part of the paraboloid, z equals to x squared plus y squared that lies under the plane z equals to 9. Okay, so let me try and graph it. X-axis, y-axis, and then z-axis. We have a paraboloid like this. z equals to x squared plus y squared, and we have a plane on top like this. This is z equals to 9, and then basically we are actually, let me graph it a little better. Good. We are looking for this part, the area of this part of the paraboloid that is under z equals to 9. Okay, so let me show you to the graph. This is z equals to x squared plus y squared, is our paraboloid, and then this is z equals to 9, and basically I'm looking for the surface area of this part of the paraboloid that is under z equals to 9. Okay, you notice that the intersection of the paraboloid and the z equals to 9 is just a circle. Okay, we need to find that as well. Okay, let's go back and start working on the question. So first I'm gonna parameterize it. This is basically z equals to f of x and y, right? So I'm gonna let x to be u, y to be v, and then z to be u squared plus v squared. And in that case, r of u and v is equal to u v u squared plus v squared, where u and v are in where? Actually, so the parameters u and v are on the projection of the intersection on the xy plane, basically here. If you just stand up here and then look at this part of the paraboloid, then you will see a circle in here, basically a disk in here. That's the region D. How can I find the region D? I need to find intersection in here because the boundary of D would be the intersection of z equals to 9 and the paraboloid. So z equals to 9 and z equals to x squared plus y squared. So the intersection of these two would be a circle of radius 3, as you see in here. So D would be the disk x squared plus y squared less than 9. Okay, very good. So u and v are in D, where D is u squared plus v squared less than 9. Okay, perfect. Now, area of the region S that I'm looking for would be the double integral of 1 and then ds over s. So what is ds? ds, we said that it would be the length of the cross product of ru with rv and then du dv or dv du. So let's find r with respect to u and r with respect to v. Okay, that is my r. Let me highlight that. Okay, so r with respect to u and r with respect to v, the cross product would be I, j, and k. So r with respect to u would be 1, 0, and 2u, 1, 0, 2u. r with respect to v, take partial derivative of that with respect to v. Derivative of this with respect to v is 0. Derivative of this with respect to v is 1. Derivative of this one with respect to v is 2v. Let's calculate the cross product in here, basic determinant of this matrix. So I get negative 2u and then j times 1 do v minus 0, so it would be negative 2v, and then for the k component it would be 1. Okay, so the length of that would be my ds, so it would be negative 2u squared plus negative 2v squared plus 1 squared and then du dv, which I can write this as dA. So I get 4u squared plus v squared plus 1, and then dA. Okay, so the area is equal to what? Area of S is equal to the double integral of 1 ds is 4u squared plus v squared plus 1, and then dA over the region that my parameterization is defined on, and the region would be this. So it would be u squared plus v squared less than 9. Okay, now since I have the double integral over a disk, I'm gonna switch into polar. So switch to polar. So when I switch to polar, what do I have? I have what? The double integral u squared plus v squared less than 9. So r from 0 to 3, and then theta from 0 to 2 pi would be the region of my integration. If I want to just explain it very quickly, let me just graph it. This is uv plane, and then I have u squared plus v squared less than 9, which would be a circle, a disk of radius 3. So this is the region, and then for r, to find the bounds for the polar coordinate, I need to have a ray, and the ray starts at origin and it goes up to 3, and then to get the full circle it would be from 0 to 2 pi. And then what is next? I need to transform my integrand into polar, so I get 4u squared plus v squared would be r squared plus 1, and then dA would be r dr d theta. Okay, I need to calculate that. I'm gonna use u sub for this, u substitution basically. I'm gonna take u as whatever that I have inside the square root, and then du would be 8r dr. Okay, so this integral that I have in here would be square root of u, and then du divided by 8. Okay. So I'm gonna take the integral. This would be u to the power of 1/2, so u to the power of 3/2 divided by 3/2 times 1/8, and then d theta. Okay, so from 0 to 2 pi, let's basically plug back 4r squared plus 1 in here, 3/2 over 3/2 times 1/8 d theta. Okay, and don't forget that r should be from 0 to 3 d theta. Okay, so plug in r equal to 3 in here, so I get 9, and then I get 37 to the power of 3/2, and then I have 12 in here, and then plug in 0, I get 1, so minus 1/12, and then theta from 0 to 2 pi, the answer would be 2 pi divided by 12 square root of 37 cubed minus 1. Okay, that's the answer for this question, the surface area of the region of the paraboloid under the plane z equals to 9. Okay, so we studied two applications. One was finding the tangent plane to, let me show it to you, the tangent plane to a surface S using parametric equation of the surface. And then the next one, we found the area of a surface S. On the next video, we're gonna talk about double integral over surface S, which we call it surface integral.